Thank you very much for having me. Look forward to talking about the SpaceX Mars architecture, and what I really want to try to achieve here is to make Mars seem possible, make it seem as though it's something that we can do in our lifetimes, and that you can go. And is there really a way that anyone could go if they wanted to? I think that's really the important thing. So, I mean, first of all, why go anywhere, right? I think there are really two fundamental paths. History is going to bifurcate along two directions. One path is we stay on Earth forever, and then there will be some eventual extinction event. I don't have an immediate doomsday prophecy, but it's eventually, history suggests there will be some doomsday event. The alternative is to become a spacefaring civilization and a multi-planet species, which I hope you would agree that is the right way to go. Yes? That's what we want. Yeah. So how do we figure out how to take you to Mars and create a self-sustaining city, a city that is not merely an outpost but could become a planet in its own right, and for us, thus we could become a truly multi-planet species. Sometimes people wonder, well, what about other places in the solar system? Why Mars? Just to sort of put things into perspective, this is an actual scale of what the solar system looks like. So we're currently in the third little rock from the left. That's Earth. Yeah, exactly. And our goal is to go to the fourth rock on the left. That's Mars. But you can get a sense for the real scale of the solar system, how big the Sun is, and Jupiter, Neptune, Saturn, Uranus, and then the little guys on the right are Pluto and friends. This sort of helps see it not quite to scale, but it gives you a better sense for where things are. So our options for becoming a multi-planet species within our solar system are limited. We have, in terms of nearby options, we've got Venus. But Venus is a high-pressure, super high-pressure hot acid bath. So that would be a tricky one. Venus is not at all like the goddess. This is not in no way similar to the actual goddess. So it's really difficult to make things work on Venus. Mercury is also way too close to the Sun. We could go potentially on one of the moons of Jupiter or Saturn, but those are quite far out, much further from the Sun, a lot harder to get to. It really leaves us with one option if we want to become a multi-planet civilization, and that's Mars. We could conceivably go to our moon, and I certainly have nothing against going to the moon, but I think it's challenging to create become multi-planetary on the moon because it's much smaller than a planet. It doesn't have any atmosphere. It's not as resource-rich as Mars. It's got a 28-day day, whereas the Mars day is 24.5 hours. And in general, Mars is far better suited to ultimately scale up to be a self-sustaining civilization. So just to give some comparison between the two planets, that they're remarkably close in a lot of ways. In fact, we now believe that early Mars was a lot like Earth. And in fact, if we could warm Mars up, we would once again have a thick atmosphere and liquid oceans. So, but where things are right now, Mars is about half again as far from the Sun as Earth. So still decent sunlight. It's a little cold, but we can warm it up. It has a very helpful atmosphere, which, in the case of Mars being primarily CO2 with some nitrogen and argon and a few other trace elements, means that we can grow plants on Mars just by compressing the atmosphere. And it has nitrogen too, which is also very important for growing plants. It would be quite fun to be on Mars because you'd have gravity, which is about 37% that of Earth. So you'd be able to lift heavy things and bound around and like have a lot of fun. And the day is remarkably close to that of Earth. And so we just need to change that bottom row. Because currently we have 7 billion people on Earth and 0 on Mars. So there's been a lot of great work by NASA and other organizations in early exploration of Mars and understanding what Mars is like, where could we land, what's the composition of the atmosphere, where is there water, or ice, I should say, and so we need to go from these early exploration missions to actually building a city. The issue that we have today is that if you look at a Venn diagram, there's no intersection of sets of people who want to go and can afford to go. In fact, right now you cannot go to Mars for infinite money. Using traditional methods, if taking sort of an Apollo-style approach, an optimistic cost number would be about $10 billion a person. So for example, the Apollo program, the cost estimates are somewhere between $100 to $200 billion in current year dollars. And we sent 12 people to the surface of the moon, which was an incredible thing, and I think probably one of the greatest achievements of humanity. But that is a steep price to pay for a ticket. That's why these circles only just barely touch. So you can't create a self-sustaining civilization if the ticket price is $10 billion a person. What we need is to move those circles together. And if we can get the cost of moving to Mars to be roughly equivalent to a median house price in the US, which is around $200,000, then I think the probability of establishing a self-sustaining civilization is very high. I think it would almost certainly occur. Not everyone would want to go. In fact, I think a relatively small number of people from Earth would want to go, but enough would want to go and who could afford the trip that it would happen. And people can get sponsorship, and I think it gets to the point where almost anyone, if they saved up and this was their goal, they could ultimately save up enough money to buy a ticket and move to Mars. And Mars would have a labor shortage for a long time, so jobs would not be in short supply. So it is a bit tricky because we have to figure out how to improve the cost of trips to Mars by 5 million%. So this is not easy. And I mean, it sounds like virtually impossible, but I think there are ways to do it. This translates to an improvement of approximately 4.5 orders of magnitude. These are the key elements that are needed in order to achieve the 4.5 order of magnitude improvement. Most of the improvement would come from full reusability, somewhere between 2 and 2.5 orders of magnitude. And then the other 2 orders of magnitude would come from refilling in orbit, propellant production on Mars, and choosing the right propellant. So I'm going to go into detail on all those. Full reusability is really the super hard one. It's very difficult to achieve reusability for even an orbital system, and that challenge becomes even substantially greater for a system that has to go to another planet. But as an example of the difference between reusability and expandability in aircraft, and this you could actually use any form of transport. You could say a car, bicycle, horse. If they were single use, almost no one would use them. It would be too expensive. But with frequent flights, you can take something like an aircraft that costs $90 million, and if it was single use, you'd have to pay $500,000 per flight. But you can actually buy a ticket on Southwest right now from LA to Vegas for $43, including taxes. So that's I mean, that's a massive improvement. Right there, it's showing a 4 order of magnitude improvement. Now, this is harder. The reusability doesn't apply quite as much to Mars because the number of times that you can reuse the spaceship the spaceship part of the system is less often because the Earth-Mars rendezvous only occurs every 26 months. So you get to use the spaceship part roughly every 2 years. Now, you get to use the booster and the tanker as frequently as you'd like. And so that's why it really makes a lot of sense to load the spaceship into orbit with essentially tanks dry and have it have really quite big tanks that you then use the booster and tanker to refill while it's in orbit and maximize the payload of the spaceship so that when it goes to Mars, you really have a very large payload capability. So, as I said, refilling in orbit is one of the essential elements of this. Without refilling in orbit, you would have a half order of magnitude impact roughly on the cost. By half order of magnitude, I think the audience mostly knows, but what that means is each order of magnitude is a factor of 10. So not refilling in orbit would mean a 500% roughly increase in the cost per ticket. It also allows us to build a smaller vehicle and lower the development cost, although this vehicle is quite big, but it would be much harder to build something that's 5 to 10 times the size. It also reduces the sensitivity of performance characteristics of the booster, rocket, and tanker. So if there's a shortfall in the performance of any of the elements, you can actually make up for it by having 1 or 2 extra refilling trips to the spaceship. So it's very important for reducing the susceptibility of the system to a performance shortfall.